So here we are in the driver software that I wrote for the UART, for the 18 mega 328 UART, or USART, USART, and I called it UART.z. And I will make this code available at some point. Well, it'll be available on my GitHub site by the time you see this video. Quickly running through this, I include some of the normal includes. Actually, this is the .h file that's associated with this driver code, and it looks like this. And I just defined a bunch of stuff in here, a bunch of constants that we'll need. Parity, number of stop bits, the number of character bits, and some errors. Some error codes, and I'll show you how they work. First thing I've done is declared a variable. It's 1 byte, 8 bits, and there's just a bunch of bits in it. And I declared it as a structure, or a union. And I've talked about unions and structures before, but this allows me access to these individual bits in a much easier way than having to do a shift and rotate and ANDing and ORing. You just access them. I'll show you how it's done in the code. And the compiler figures out what bits to look at and what ANDing and ORing has to be done to get the bits out. And these are just the, well, these three here are the errors that can occur. We talked about the frame overrun and parity errors. Now I wrote this general purpose, so this will accommodate all types of UART that you set up. But of course, in this case, we're not going to use much of that. So I have a function here called UART init, and it takes 4 parameters: rate, size, parity, and stop. So rate is the bit rate in bits per second, also known as the baud rate. Size is the frame size, which can be any of these sizes up to 9 bits. Parity, none, odd, or even, and then the number of stop bits. So I've declared a temporary register here, and the first thing I do is I clear our status right here, USART status. And I access the whole byte by going .val. If I just wanted to clear, say, rx9, I would just say .rx9 equals 0, and it would just clear that one bit. But in this case, I wanted to clear all of the bits in one instruction, and that's how I do it. Now the first thing I want to do is set the USART mode, and in this case it's just a UART, so it's asynchronous only. And so I look at the control status register C, and I AND in these 2 bits here. And I make it asynchronous. So let's look at USART, or yeah, the UART status register C, which would be here. Whoops. C, and it's these 2 here that I'm making those 2 0. Oops, no, wrong. Not these 2. These 2 here. I'm making these 2 0. They come up as 0 when it's reset anyway, so I didn't probably need to actually write this instruction here, but it just guarantees that those are going to be made 0. The next thing I do is I look at the parameter size, and by whatever value size is. Now when you call this, you need to fill in size, rate, size, and priority, and stop as well, but rate is just a number you give it, the number of bits per second. Size will come out of here, and it will be one of these defines. And it just looks at what value it is to determine what register, or what bits in what registers to set up to determine the size. Now remember, I showed you in this, there's 2 bits in this register, and in the status register B there's 1 more bit. So that's why in the software register B is affected here as well. Now that takes care of the size. Next thing is parity, and again, parity code for parity comes out of here. So you'd select one of these when you invoke or call UART init. And again, the program just looks at that parameter, and then it does a switch statement here to determine what to do. And in status register C, if you look back at it here again, register C, our parity would be these 2 bits. So we're setting up these 2 bits using this bit of code here to determine what the parity is. With no parity, parity none, I'm clearing them both, parity even. Bit 0 is low, bit 1 is high, and then when the parity is odd, both of them are high. The last thing I do in here is I look at the stop bit. Again, the stop bit comes out of UART.h, and it's either 1 or a 2. And then here it's just simply, if it's if you look at what 1 and 2 is, 0 and a 1. So if stop bit 1 is a 0, it'll execute this one here. If it's a 1, it'll execute this one here. And all it's doing is setting or clearing a particular bit in the status control register C, which is this one. Last thing we do is we generate or come up with a value to put into the baud rate register. Now, this is important here. You must define this somewhere in your code, and I've shown you before in other videos of where to define it in the project properties. But somewhere, if you want to rewrite this, you could put it, say, in UART-H and put fCPU equals whatever the frequency of your CPU is, which is, in the case of an Arduino, it's 16 megahertz. So you write down 16 followed by 6 zeros, and that would give you the value of fCPU. The first thing it does is it looks at if fCPU is really low, it's automatically going to set up this baud rate by using the 2 times clock rate. And here is a calculation that takes fCPU and divides it by the baud rate that you've defined when you called this function. Now we'll go back up there. And then puts it into this temporary register. And then what I do is I put it into, this is a 16-bit register, so I have to write the high and the low registers for the baud rate register. And I do that by shifting the upper part down by 8 bits, so the upper byte gets shifted into the lower byte, and I put that into the high register. And then I take the lower byte of the baud rate register not shifted, and I put it into the low register. And then here I set that 2 times bit because the fCPU is quite low. But in our case, because fCPU is well above 200, I think that's 200 kilohertz. Yeah, is that 200 kilohertz or 2 megahertz? No, it's 2 megahertz. So if it's above 2 megahertz, it will execute this part here. It'll do the same division again, but this time I'm dividing it by 16 instead of by 8, and then I'm clearing that 2 times register bit. And then the last thing I do in this function here is I enable the transmit and the receiver by writing these bits to status and control register B, which is these 2. And that's it for UART init. If I want to send a character out the UART, I call this function called putChar, and then I put the character that I want to send into the parameter. And the first thing it does is it polls this bit UDRE0 in the UART control register A. So it's this one here, and what it's doing is looking at this bit here. Remember I said that if the data register is empty, the bit will be set. If it's not empty, the bit will be cleared. And so what I'm doing here is waiting until the bit is set. And it's going to sit here forever. If something goes wrong, or if you forget to enable your UART and turn it on, and you call this function here, the code will lock here, will block here permanently. And so it actually has to, or if you've disconnected the cable going to it and there's no data coming into your UART and you've done your initialization properly, but there's no data coming in, this, oh sorry, I'm looking at the wrong one. This is put car, so this is sending a character out. So after the data after a byte of data has been sent, the data register will be empty, so this bit will be set to 1, and then this while loop will fail, and it will end up in writing this character here into the data register. Now after you've done that, the bit will be cleared, and if you ever went back into this again, this loop will continue to execute because the bit is clear. And then once the data has been transmitted out, this while loop will fail, and you'll end up in writing the character to the data register. Now the microcontroller can write to that data register way faster than the data register can shift out any kind of data that you put in there. I said at 9600 bits per second, it's 104 microseconds per bit, so there's 10 bits that have to be shifted out of there, including the start bit and the stop bit. And so that's just over a millisecond. Microcontroller can execute thousands of instructions in one millisecond. So it's going to hang in this loop for quite a while until the data register is empty. But this one, well, again, if you've forgotten to enable your UART, this bit may not be set, and this while loop may run forever, and so you may block here. That's one of the problems of the way I've written this code, is it's completely blocking. But when things are set up and working properly, this code works just fine. But also realize too that while it's waiting for the transmit register to be empty, your microprocessor is doing nothing else unless there's interrupts enabled and it's doing something outside in interrupt routines. But if it's not interrupting, not being interrupted, it's not going to do anything else. It's going to sit here wasting time. Similarly, we've got this function called getChar, which means get the character that's been received from the receive register or the data register. And again, it sits here waiting until there's actually data in the register. And if the data never arrives, it's just going to sit here forever, and it's never going to stop. It's never going to leave this loop. So you got to watch how you set things up here. Again, if everything is set up properly and working properly, this is not a problem. It's just going to sit here waiting till the next character is in. And then the next thing it does is it hasn't even done anything with the character it's received yet. It's just going to check these statuses and these status bits to see if there was any kind of an error. And what it does is it just sets the appropriate bits in this structure over here that I showed you earlier, and this gets stored locally here in this function, and it can be read later if you need to. Nothing gets done with it. And then the last thing it does is it returns whatever value it got in the data register. And a couple more functions here. Let's go to put string here. This one will just write out a string of characters. So you've got a pointer here, which is a string, which is an array of bytes. And the way you set up these arrays of bytes is that the last character in it is a 0. That tells you, this program or this function here, that you've reached the end of the string. That's important to put in there. And so what it's doing is going through the string one character at a time, starting at the beginning, and if it's not a 0, then it's just outputting the data to the transmit register. And in fact, the code here is identical to the code that I used for put car up here. So it'll just sit here humming around through this loop, going through one byte at a time in the string until it reaches a 0, and then it stops, and that's the end of it. It's finished, and it's output the string. This function here is similar, except that the string is now stored in flash and not in RAM. So this one here, it expects the string to be in RAM. And it does the same thing here, except there's a function you have to call called program read byte. And that just means read the byte out of the program register, and this is or out of the program data, and this is the address of the register. And each time through this loop it gets incremented. And similarly with this one here, my index, this is the index to my loop, or to my basically the address, the byte in the string, and I just increment it each time through. Same thing here. What else we got here? Some of these are really not. This one I stuck in here. It just puts a character straight into the data register. I don't think I've ever used it. This one here is if you've got an error, you want to see if there's any errors, you can read status. It returns the byte, and then you can look at the bits in the byte to see if there's any kind of an error. And so this one also clears it, clears the status register. This one here is if you don't want to block while you're waiting for a character to come in, you can do this. You can just call this, and what it does is it looks for all the errors and looks for any errors and returns a value, an error code if you get an error. If there's no errors, it looks to see if there's a character available in the receive register, and if so, if that's true, if it is, then it returns this value. UART is available, which means there's a character available in the UART. And so this will never block. It will just tell you if there's a character available. And if there is one available, then you can call getChar up here and read the character without having to block. This is a way of reading the serial data without actually blocking. Beyond here, there's just a bunch of small functions to set or to enable or disable the various interrupts. Now let's look at the code for generating the direct digital synthesis. Ugh, it's a hard word to say. You've seen most of this already. I've added a function prototype here because I got another function I've declared below my main loop, and it wouldn't be visible unless I told the compiler that it's there. I could have put it above the main loop because that function gets called in main, but I just find it easier to put them after main because it's just a better place to put them, at least in my opinion. Let's get to that in a minute here. A couple of declarations here. Well, let's go back. So I've included my own UART.h that I just went through with you just momentarily. I defined what a carriage return and line feed, what the ASCII characters are for those, ASCII codes for those. I think we've seen these before. We've seen the sign table before. I am having trouble remembering exactly what I did because I looked back on the date here, and it's back in November when I did this the last time. So this would be about the last time I did a video. I've been so busy during the winter here with my ski guiding work and so forth, I didn't have time to do any more videos. So bear with me as I try to remember what I was doing here. So I think a lot of the stuff we already talked about. This is the timer 2, which sets up our reading bytes out of the sign table and outputting them to the PWM and or to the ladder, R2R ladder. And so that's what's happening here. We're outputting to the output control register 0. And so timer 0 is being used to generate a PWM, and then I'm just outputting a value out of the sign table to the output control register, which determines the duty cycle of the PWM. Now I could only connect my ladder, R2R ladder, to a 6-bit port, and so I just made both of these look the same, whether it's using the PWM output or the ladder output, and I just simply clear the last 2 bits of the value you get out of sign table, because that's all I can do with the port C here with the ladder. So what I do is I take the value that I've read out of the sign table and I just right shift it by 2 and then output it to port C. And that's all it gets done in that register, or in that interrupt interrupt service routine. So back in main here, I think I've talked about this already, how timer 0 is set up, how timer 2 is set up. Now here is something new. This is the UART init function that I described just a moment ago, and so these are the 4 different parameters. There's your bit rate at 9600 bits per second, the character size, the parity, and the stop bit. And so I enable the interrupts, and then all I'm doing in while 1 here, because remember before our while 1 loop did nothing, it was blank. Now I've added this one function. called serial frequency, which is just below us here. So this is how we are using a UART. Now, how the user actually makes this work is you simply type a digit, a 0 through 9, on the computer. You set up your computer and hook it up through a USB to serial connector or a USB to serial converter chip, and so that goes between your microcontroller and the PC. And then you load up or fire up a terminal program. Teraterm or Hyperterm. There's a couple of different ones that you could use. Putty is another one, P-U-T-T-Y. And they just turn your computer into a dumb terminal. You just type a character, it goes out. Anything that comes back from the end of the serial port will be displayed on the screen. And so that's how you can set the DDS frequency, is by typing the frequency you want and then hitting the enter key. So the way this serial frequency works, it gets called every time, many times. It gets called very quickly. As fast as the while one loop runs, this set serial frequency will be called. And the first thing it does is it calls the function I talked about here in UART.c called UART available, where it just simply looks at, what are we here, UART available. Looks at the various status bits to see if there's a byte if a byte has been received, and it returns right away. So if it returns with this value in the return value or the return parameter, that means there's a character is waiting. The character is here. Let's look at the other end of the if statement here. If that statement fails, there was no character waiting, it does nothing. It finishes. So serial frequency will terminate. So in the while loop here, most of the time when you call this, it's going to return with having done nothing, because there was no character available. If there is a character available, get it, and we store it temporarily in this variable called C, and immediately output it back to the terminal. And remember when I explained putchar, it's going to I think it will sit here. No, it won't actually. Putchar, it will just output it right away. Where are we? Putchar. Yeah, putchar will execute right away, or will return right away, because the data register will already be empty. So as quickly as you can get the character, it's going to get output again back to the terminal, and that gives you the echo so that you can see what you have actually typed on the screen. The next thing it's going to do here is it takes that character and decides whether it's a valid character. Did I push a digit, like 0 to 9, or a carriage return, or did I push something else? If I push the letter A, for example, this will fail. This will evaluate as not true, and you'll end up down here, not an acceptable character, and I just reset the whole process. I'll explain what buff and I are in a moment here. So what this statement here is checking to see if it's a valid character between 0 and 9, or a carriage return, and that's all it does. If it's not a carriage return, that means it's a character that's a 0 through 9. So what we're going to do is we're going to store it in buffer, or in buff. So where are we? Buff here is a series of 6 byte variables put aside, and I made it static, so that what it means is it doesn't go away when serial frequency finishes operating, or when serial frequency returns. And so it'll always be stored. It's just that you can't see buff anywhere else outside of this function. Same with this I. It's an index or a counter. It's also static because I want to remember it between calls. Same with the buff. I want to remember it between calls to set frequency. So if it was a valid character but it was not a carriage return, we simply store it in buffer and point to the next available space in buffer, in buff. And that's the end of it. The next thing I do after that is I check to see if I has incremented to 5, or if the character that I just received was actually a carriage return. And so if I is greater than 5, let's see here. No, if I is equal to 5, okay, if I is greater than 0, well, I will always be greater than 0. I'm not sure why I did that. Anyways, I could just say if I is equal to 0. Doesn't matter. This logic here is actually kind of weird. It still works, but it's I only just noticed this now. Anyways, it's very simple. What I'm doing here is if I has reached the end of the buffer, because I'm only allowing 5 characters in it, so I is equal to 5, which is pointing to the next available space in buffer, which is 6. But I'm not going to put a character in there because I already got 5 characters, so I have to terminate this string, and I talked about that when I was describing UART. So I just put a 0 in there, so that's a null terminator, and it allows the we're going to use put string here, UART put string, and so what it's doing is scanning through the buffer. So you pass as the parameter here an address or a pointer to that buffer, and then this simply scans through that buffer, printing character or sending those characters it sees in the buffer out the serial port until it reads a 0. And so that's what I'm doing here, is putting in the 0 there to tell put string to stop outputting characters. If you don't put that 0 in there, it's just going to keep going until it finds some random 0 in RAM, and it could produce some pretty weird results. And so buff is now a string of characters, and what this function does is A to I, ASCII to integer. So what it does, it takes an ASCII string and does a conversion and makes it into an integer. So I just tell it what string I want to convert, and it returns the value in here. So phase inc temp was declared up here, somewhere up here. There it is here. No, it was not. Sorry, wrong. Phase inc temp was defined here. It's only a temporary buffer. And the reason why I did that, because I don't want to affect the actual phase increment register. I want to do something to this first. I have to do a test. So if phase inc temp is greater than our maximum frequency, I just make it to the maximum frequency. And that way it doesn't go any higher. Because remember I showed you how I couldn't get the frequency any higher than a certain frequency. So I just put a stop to how high you can actually make the frequency go. So if, I think it's 15, yeah, it's 15 kilohertz. So if you typed in 15001, this would, a phase inc temp would only get will only be as big as 15,000 or whatever value it is. If it's greater than that, it gets set to that value. If it's not greater than that, then it's okay to use it. And all I do here is I do a little bit of math to figure out the index, and I put it into phase inc, which is the global variable that we declared up here, right there. And remember, it gets used to determine what value we take out of the sign table here. Then I reset the pointer. I make a buffer a null string, so at the very first location of buff I put in a 0. It doesn't matter that 1, 2, 3, 4, and 5 have something in them. If you try to do something with this string, the first thing it's going to see is a null character, and it's going to say, oh, the string is empty, there's nothing to do. And then I reset my pointer to 0 as well, and I'll put a carriage return and a line feed to the terminal, so you can see that you've entered the new frequency. And that is about it for how this works, how we use a couple of functions in UART.c to implement something kind of neat here, where you can just type in a frequency and get my direct digital synthesis system to work, to output the frequency. So here is the setup for controlling the DDS with the serial port, and you'll notice that I haven't used a USB to serial converter module because the Arduino already comes with one. In fact, if you look at it, this chip here, which is the USB to serial converter module for the Arduino, is exactly the same chip as here, except now it's hardwired up to the AT Mega and to the USB port here. If I didn't have anything like this on my project, I could quite easily use something like this. You just hook it up the same way. There's two wires that come out of here that go into the microcontroller for the TX and the RX, and plus you have to provide power and ground with this guy as well. But that's how you can control a microcontroller project, not just my DDS project here, but any microcontroller project with a serial port. So I hope that you got something out of this. Check out my GitHub site. The software that I use to make this work is uploaded there, so you'll be able to use it and play with it. I encourage you to download a copy of it and then look through it as you're reading or as you're watching my video, and then you'll get a better understanding of how the software actually works. And as I always say, the way I wrote the software isn't necessarily the best way to do it. It's just the way I did it and the way I came up with it at the time. It works, but there's ways you can make it improved. Anyways, I hope you got something out of this, and thanks for watching.